Hello. In this video, we're going to talk about test selection. In statistics, we have two major types of statistics. We have descriptive, which we've largely covered. These are things like the mean, median, mode, frequency that are describing or summarizing the data. And the second, which is what we're going to largely focus in this video on, are inferential statistics. And within inferential statistics, we're going to talk about comparative tests and associative tests. So as I mentioned, we have two major types of statistics. We have the descriptive, where we're organizing, summarizing the data. So we're trying to often describe what is the average performance within a set of scores, what is the general performance within a set. And so we're often using the mean, the median, or the mode to do that. And then the second type is inferential. And with inferential, we don't want to just know about the sample that's in front of us. We don't want to know just about the data we already have. We want to take that data and we want to begin to generalize, extend beyond that data. And so what we're trying to do is answer questions through analyses and interpretation. So not just what was the average for this group, but what average would we likely find if we did this again, for instance? And what would be the likely range of scores? And then, is there some other score that falls within that range or not? And if not, then we could begin to say that this group that we have is different from that other score. We'll talk more about that whenever we get into z-tests. We'll make it a little bit more specific. So if it seems a little bit nebulous right now, that's fine. We're going to make it really concrete in about a week. So as we move into inferential, there's two types or two groups of inferential statistics. There's comparative, and with comparative, we are comparing groups to see if there's a difference between them. And we can compare a population to a sample, we can compare two groups, we can compare 3, 4, how many ever groups is needed. And we'll talk about how really the number of groups that we're comparing is one of the major things that lets us decide which test among the comparative tests we should be using. With associative, here we're looking at the association or relationship between two or more variables. And so among the comparative tests, one sample z-test allows us to compare a group or a sample to the population when the variability within the population is known. So typically we need the variance or the standard deviation of the population. And variance is represented by sigma squared. Standard deviation is represented by sigma. And if it's been a while since you've practiced APA style, because those are Greek letters, we're not going to italicize those. Although typically when we're doing abbreviations for statistics, especially if we're using traditional Roman lettering, then we are going to italicize that to denote that it is a symbol for that value. With one sample t-test, here we're going to compare a group or a sample to the population, and in this case the population variance or standard deviation is not known. So we don't have a variability value from the population. Maybe we don't have the original data, maybe we can't calculate it, maybe it wasn't provided. We still need the mean of that population because we're going to compare the sample mean to the population. But what we're going to do if the population value is missing on variance or standard deviation is we're going to use the sample value as an estimate of that variability. And so we still need either the standard deviation or variance from the sample to be provided, or we need to be able to calculate it. And if we can't either have it provided or calculate it, potentially we can't do any of these tests at all. If we have two groups or two samples or two conditions and we want to look at them and they're unrelated, they're not connected to each other, matched, paired with each other, then we can do an independent samples t-test. And it's often easiest to know, what do I mean by they're not matched, paired, connected to each other, by looking at the next test. With the dependent samples t-test, they are related in some manner. They are matched or paired, or we have what's called a repeated measures design, where we have the same individual in multiple conditions or the same individual at multiple times. Well, that person, if they're in each of our conditions, is dependent on themselves. Their score is related to their own score between time 1 and time 2. And so what we're really interested in is the change from time 1 to time 2, or the change between the two conditions. So often we'll do something in the interim between those two time points, and we're looking at what did the thing that I did or the researcher did in between time 1 and time 2, how did that influence the outcome? And so because we have the same person at both points, there is some shared variability within that person. And what we do is we really partial that out. And when we get into the whole introduction to dependent samples t-test, that's where we'll show you mathematically how does that work and how do we deal with that within subject variability. Some people are scoring high, some people are scoring low. We really don't care about that. What we care about is the person who scored high still going up in their score from time 1 to time 2? And is the person who scored low going up in their score from time 1 to time 2? And if both of them are going up and we see that consistently across the sample, then likely we would say that there's been a change, a significant difference from time 1 to time 2. And then the last comparative test is the one-way analysis of variance, or the one-way ANOVA. And here we're comparing 3 or more groups. In fact, you can actually compare 2 groups with the one-way ANOVA, but because we already have the independent samples t-test, we typically use that when we have 2 groups, and we use the one-way ANOVA when we have 3 or more groups. And when we get to that, we'll talk about what's called a within subjects ANOVA and a between subjects ANOVA. And basically, the within subjects ANOVA is like the dependent samples t-test. So now, instead of just before and after an intervention, I can look at somebody's progress across multiple time points. So if somebody comes in for treatment for depression, I can get their baseline when they initially come in for their first appointment. I can look 4 weeks later, have they shown improvement? 8 weeks later, have they shown improvement? And so now I can do 3 time points as opposed to just 2 time points. Additionally, if I wanted to look within families, for instance, well, with the dependent samples t-test, I can look at a brother and a sister, or I can look at 2 siblings. With the one-way ANOVA, I could potentially do 3 or more siblings altogether for that. Moving from comparative test to the associative test. With the associative test here, we're trying to assess the relationship or association between 2 or more variables. And to differentiate between the 3 associative tests, one of the things you want to focus on is what types of variables do we have. So you've done the homework on measurements, levels of measurement, and you've looked at nominal, ordinal, interval ratio. That skill that you've already developed is going to help you to determine which of these tests is most appropriate. So with a chi-square test, we can evaluate the association between 2 categorical variables. So by categorical, that's encompassing nominal and ordinal together. And so if I have a nominal with a nominal, or a nominal with an ordinal, or 2 ordinal variables together, and I want to look at how are these associated, basically what I'm looking at is, does group membership on one variable relate to group membership on the second variable? So if I'm looking at men and women and likelihood of staying in college, for instance, or completing college, I have a grouping variable, men and women, and then I have a second grouping variable, did you end up graduating from college or not? And I'm looking to see, is there an association? So do women, for instance, tend to graduate at a higher rate, or are they more likely to graduate? So are they more represented within the graduated group as opposed to the not graduated group? And again, mathematically, we'll show you that when we get to that week. With bivariate correlation and bivariate regression, in contrast, instead of using categorical variables, now we're typically using continuous variables, or a continuous variable with a dichotomous variable or a binary variable. With continuous variables, this is again an encompassing term that we use for interval and ratio types of data. And so what we really care about is the continuous nature of the data, meaning that there's this underlying continuum, and instead of just units of measure or categories of measure, we can refine our units of measure. So you can say that somebody's height is 5 foot 10 inches, for instance, but really we could be more refined in our units of measure. We could say they're 5 foot 10 and a half inches, or we could shift into smaller units and be more refined in that way. So if we measure it in millimeters as opposed to centimeters, and that would allow us to do that as well. And so there's really this underlying continuum where, given enough time, money, energy, we could measure that variable at a more refined unit of measure. With bivariate correlation versus bivariate regression, the major difference is the regression implies directionality, because with a regression, you are saying that one thing predicts another, or that one thing causes or leads to another thing. And because of the nature of the data and the way that the data is used, then it better fits when the hypothesis has either stated that there's a directionality, A causes B, or at least strongly implies it, where maybe one of your variables is a stable personality characteristic and the other variable is kind of a momentary decision, for instance. Well, it would make sense that the stable personality characteristic is influencing your decision in the moment. And maybe the outcome of that does have some influence on later personality characteristics, but in that moment, your measure of personality is relatively stable, has developed across time, and importantly, we have temporal precedence. That personality has developed before the moment in which you were deciding on the action. And so, because of that, likely the researcher has stated that A causes B, personality leads to this decision, but even if they hadn't, it's kind of implied by the nature of the variables themselves. Now, sometimes we do regression and it can't inherently prove causality. Just because A and B are related within the regression and it is significant, and we'll talk about what does that really mean later, but just because that happens doesn't mean that you can truly say, well, my data proves that A causes B. We need to meet a number of criteria, and I'll talk about those when we get to it, but temporal precedence is one of those criteria. It doesn't make any sense to say A causes B if in fact B came before A, for example. So, broad overview visually of what we've talked about so far. We're looking at inferential statistics. Within inferential statistics, we have the comparative types of statistics on the left-hand side in gray. We have the associative statistics on the right-hand side in blue. And for our one sample z-test, what we're doing is comparing a population to a sample, and some measure of variability from the population is known. So we either have sigma or sigma squared, which represent the standard deviation or the variance for the population. With a one sample t-test, when we don't know the variability of the population, we can use the sample variability as an estimate of that. And that does still require, though, that we either know the sample variability, again, standard deviation or variance of that, which is often represented as S or SD for the standard deviation, depending on if you're looking in a stats book or if you're looking in a journal article, or it's represented as S squared for the variance. But we have to either know that or be able to calculate it in order to do the one sample t. With the independent samples t and the dependent samples t, we're comparing two samples or two conditions. And in the case of the independent samples t, there's no matching, pairing, repeated measures. We haven't used the same person twice. We haven't used a brother and a sister. We didn't match people on their SAT scores. So in that example, it would be possible that when students come in, we match all of them on their SAT scores, and then I take the two highest SAT scores, for instance, and I put one person into a group that has some additional training and education, and I think that that's going to help them continue from their first year of college into their second. And then the other person who has one of the top two scores goes into the other group, the control group, where they just go to their classes, they do their normal thing. They don't have that additional weekly meeting or weekly training throughout the first semester or something. And then I look to see, did that training benefit one group over the other? Well, the nice part is we know that if you're relatively prepared for college, you tend to be more likely to succeed, do well in college, feel confident in your abilities, and then continue. Well, if I already know that that is a factor that is related to your likelihood to continue into your second year, then by matching these individuals on that factor, I've now taken away one of the sources of variability. I've controlled for that source of variability. And that would be an example of a dependent samples t-test where we have matched them, we've paired them on that variable before we even started the study. And then with the ANOVA, whenever we're comparing 3 or more groups, then it's going to be an ANOVA. And if those groups are dependent on each other, related to each other, we have the same person at 3 time points, for instance, then it would be a repeated measures ANOVA or a within subjects ANOVA. It's called both, either. And by contrast, if we had 3 different people in 3 different conditions, so going back to that example, we take individuals and a third of them get some type of training on social skills, a third of them don't get any additional treatment, and another third of them get some extra tutoring. So basically, we're looking at no training, academic training, and social skills training, and we're looking to see, are we more likely to retain students, or maybe are those students likely to succeed in regards to GPA or some other indicator between those 3 groups, and then we can make the comparison. When we look at associative, again, the thing that we're really interested in is the types of variables that we're working out, the level of measurement of those variables. When we're looking at the association between 2 categorical variables, either nominal or ordinal variables, then we're going to perform a chi-square test. If we're looking at continuous variables or a continuous variable with a dichotomous variable or a binary variable where there's 2 options like men, women, if we're looking at biological sex, then a bivariate correlation or a bivariate regression would work. And the distinguishing factor is there some type of assumption of directionality, or has the individual stated that there should be a directional relationship? If not, we can just use a bivariate correlation and say, are these things correlated? Are these things associated? If there is a directionality, then we could use the bivariate regression to say, does A cause B? Is A predictive of B? In addition to looking at this visually, we can also take kind of a step-by-step approach. So you can read through a research example or a research vignette, and we can identify the research question or the hypothesis as our first step. Basically, what we're trying to get a sense of is what are the variables involved and what is the relationship that I'm looking at for those variables? Am I comparing? Am I looking at the association? So then in step 2, we ask that question, okay, I've identified what the research question is or what the hypothesis is, and we are looking at, am I comparing groups or am I checking the association between the variables? If I'm comparing groups, then we go to 2A. And the next question is, well, how many groups or samples or conditions are we using? If we're using one sample or condition and we're comparing it to a population, it's either going to be a one sample z-test or a one sample t-test. And the question I have to ask at that juncture is, well, is the population variability, either the standard deviation or the variance, known? If it is, then I'm going to do a one sample z. If it's not, then the next question is, well, can I use the sample estimate for the variability? And if so, then we would do a one sample t. If we have 2 conditions or 2 samples, then the question is, well, is there some form of repeated measures or matched pairs design being used? If so, then I'm going to do a dependent samples t, and if not, I'll do an independent samples t. And then finally, if there's 3 or more samples, 3 or more conditions, then I'm going to perform an analysis of variance. If when I get to question 2, we're not comparing groups, and instead we're checking the associations between the variables, then I would go to 2B, and I would ask myself, well, what types of variables are being used? In particular, are we using categorical variables, again, those being nominal, ordinal, or are we using continuous variables, interval ratio level variables? If both variables are nominal or ordinal, then it's going to be a chi-square test. If both of them are continuous, it would be a correlation or a regression. And again, could be a continuous with a binary variable as well. And when we get into that, I'll show you a visual of why can I perform this type of test with a binary variable and a continuous variable, and show you how even in that case I can basically draw a line, a single line, to represent that relationship, to represent that association, and thus I can still perform a correlation with that data. And then the final step is, well, if I am doing a correlation or regression, which one am I doing? And the question is about directionality. Are we saying that A predicts B? Are we saying that A causes B? If so, we'll do a regression. If not, a correlation would be more appropriate. We're just looking to see, is there some form of relationship? So you may need to go back through that a couple of times. This is the beginning introduction. And fortunately, we're going to spend the next several weeks of the semester basically going one test at a time, each lecture for an entire week. We're going to reintroduce this. We're going to go through it again. I'm going to give you more detail. We're going to practice it. And so by the end of the semester, you're going to have seen each of these tests several times. Each quiz is going to be looking at, can you select the right test? And basically the quizzes become cumulative across time, where I'm going to give you an initial homework that has you do some work to differentiate, well, is this chi-square, or is this bivariate regression, or is this correlation? And then we're going to focus on the z-test. And I'm going to give you a homework, and you're just going to be like, is this appropriate for a z-test or is it not? And is the next question appropriate for a z-test or is it not? And then the second homework, we will have covered z-test and one sample t-test. And you're going to ask yourself, should I use a z-test or should I use a t-test? And so you're going to have this opportunity to each week kind of reiterate, repractice some of the information that you've already seen, and then kind of build on it as we move forward. So if it takes you a couple of quizzes for this to click, that's fine, because I dropped some of those because that's part of the learning process. Still, we're going to practice this here. We're going to make it a little bit more concrete. So look at this first research scenario. Samantha thinks that dogs are more adorable than cats. She has individuals watch 10 videos of dogs and 10 videos of cats. Individuals rate each video from 1, not at all adorable, to 10, that's the most adorable thing I've seen this year. Don't ask Dr. Bird about measurement issues. My guess is this scale wouldn't be exactly valid, but it's cute and I'm going to keep it. So, when we look at this, our first step is to identify the research question. Here we see that Samantha thinks dogs are more adorable than cats. That's basically her hypothesis, that she expects that they will be rated more highly in adorability than the cats will be. We can shift that into a more broad research question of just, are dogs more adorable than cats? And then we can consider, well, are we comparing groups or are we checking the associations between variables? And from this, we can see that we're comparing dogs and cats in regards to how adorable they are. And so the next step is then to look at 2A. So if we're comparing groups, well, how many groups or how many samples, how many conditions is Samantha planning to compare? She's comparing two, dogs and cats. And the question then is, well, is a repeated measures or a matched pairs design used? Importantly, if not, then it's going to be an independent samples t-test. If it is, there is some type of repeated measures or matched pairs design, it will be a dependent samples t-test. What we see is that Samantha has individuals watch 10 videos of dogs and 10 videos of cats. What this does for us is, if you have somebody that's absolutely hates both dogs and cats, I've kind of controlled for that because I have their ratings of dogs and their ratings of cats. Or maybe they're allergic, and so they, as they even watch the video, they think about their allergies and everything else. And so because of that, their ratings of dogs and cats both will be low, right? And then there's maybe somebody else that they just absolutely love pet snuggles no matter what pet they're coming from. And so they're going to rate dogs and cats both relatively high. Well, this design, because we have individuals rating both the videos of dogs and the videos of cats, controls for that individual variability. It controls for the fact that some people just don't really like animals, and other people absolutely love basically any animal they touch, and it controls for that within our design. So because of that, because of the fact that we have the same person rating both types of animal, this would be best for a dependent samples t-test. Now, if I just change this one word from she has individuals watch 10 videos of dogs and 10 videos of cats to or, so she has 10 individuals watch 10 videos of dogs or 10 videos of cats, now there's no connection. There's no matching that's occurring. We're not testing the same person twice. There's no repeated fashion to this testing. And so because of that, then it would actually be more appropriate for an independent samples test if this one word was changed. So again, that's where I mentioned that throughout this, you'll see some scenarios, and Taylor's one example, where Taylor's studying the relationship between extroversion and music preference. And she studies it a number of different ways throughout the semester. And every time I change just a little thing. And what you can do as you're preparing for the exam is go back to those in-class practices where I use Taylor, and that name is always the same. It makes it really easy to compare and contrast. Well, what was Taylor doing here, and what was Taylor doing here? And why is it that when Taylor changed this piece of the study, suddenly we don't do a t-test anymore, we have to do an ANOVA. Or suddenly we don't do a z-test anymore, we have to do a t-test. And so those little changes, I'm not doing it to trick you, I'm not going to try to trip you up, but those are important. We do need to pay attention to these details, and so I'm going to try to cue you to the details to pay attention to. All right, so let's move on to vignette number 2. We need to first identify the research question, and then we'll move forward. So Samantha thinks that individuals who are more intelligent tend to rate their professors higher. We do actually find that if you score well in a class, you tend to be a little bit nicer on evals. So it's possible that just by being prepared for the class, a little bit more intelligent, maybe perform better in the class, feel better, happier, more satisfied with the end result. So she has individuals take an intelligence test. The min is 87, the max is 143. X bar here, that's the mean. So X bar is 106, standard deviation, this is the standard deviation SD of a sample, is 11. She has individuals complete a 10-item questionnaire to assess how pleased they are with their professors. Each item has a range of possible responses from 1, not at all true, to 5, very true, and the responses are summed across the 10 items so that the possible scores range from 10 to 50. So when we're looking at Samantha and her research design, the research question, right? Her idea is that individuals who are more intelligent tend to rate their professors more highly. So that's more of a statement. So it's more of a hypothesis. We can reword it a little bit. Do individuals who are more intelligent tend to rate their professors more highly? And we could even be broader than that. Is there a relationship between intelligence and professor ratings or teacher ratings? And that would be more in line with a broader research question. And then we could look at individual factors within that. So in this case, we're looking to see if intelligence, right, is related to professor ratings. So really what we're doing is checking the association between these two variables. And so our next question, that puts us at 2B within that list, that step-by-step process. Well, if I'm looking at association, what types of variables, categorical or continuous, are being used? In this case, I have intelligence, and we've talked before, anytime we're working with a standardized test, anytime we're working with like a state educational test, something along those lines, for the purposes of this class, we're just going to assume that it's continuous. And then when I get into looking at some specific examples with numbers, I'll show you how to evaluate that we have met that criteria, that we've met that assumption. But for the moment, because of the fact that this is a IQ test, it's relatively validated, it's been tested, it's been standardized, that's going to give us at least interval level data. It's going to be continuous data. And then we have 10 items that are measuring the individual on not at all true to very true. And again, when we add multiple items together, even though each individual item is ordinal, if I respond with 5, it is more true of me than if I put a 1. But is your 5 the same as my 5? We get into all those measurement issues, measurement questions. And on any given item, yes, it's ordinal scale. But when we add a bunch together, the sum, the total for those items, tends to have the characteristics of a interval measure. And again, we're going to check that later on. I'm going to show you how to do that. For the moment, though, we're just going to assume if we have multiple items in this scale, it's giving us interval level data. So we have two variables, both of them are continuous in nature, and we're looking to see, are they associated? So we're going to do a correlation or a regression. And to determine, should we do a correlation? Should we do a regression? Our last question is about the directionality. Samantha thinks that individuals who are more intelligent tend to, right, that would suggest later, right, tend to rate their professors more highly. And so we do have this directionality. And because of that, it would probably be more appropriate for Samantha to do a bivariate regression. And the only difference between bivariate and multivariate is the number of variables that we have. With bivariate, like a bicycle has 2 tires, bivariate, we have 2 variables, and we're looking to see how they're associated. How does one predict the other in a regression? That gives you a sense about these different types of statistical tests, about the comparative tests, also gives you a sense about the associative test. Again, if you're still a little hazy about some of the finer distinctions between, for instance, an independent samples t-test and a dependent samples t-test, that's fine. That's about where I want you to be. And you'll find conveniently that on homework assignments and other types of assignments, if you can narrow it down to, I know it's one of these two, for the foreseeable future, for the next few weeks, amazingly, that won't be one of the answer choices. So what that does is it allows the homeworks to help you learn the material, which, as I mentioned at the beginning of the semester, is exactly what I want them to do. You narrow it down to, it's got to be one of these two, and then one of those two is in fact not even an answer choice. What that does is throughout the next couple of homeworks, that's giving you more and more examples of, oh, okay, I narrowed it down to independent samples t-test or dependent samples t-test. Dependent samples t-test is the only one that's a choice. When I look back, oh, here's where I see the matching. Oh, here's where I see that it's repeated. Oh, here's where I see. And so that's going to give you one more example, and it's going to reinforce your learning. It's going to give you an opportunity to maybe be wrong, but not actually end up getting the answer wrong, and to then learn from that almost instantaneously. And then, of course, I'll also provide feedback on those homeworks, and especially on the homeworks. Once we get about 2 homeworks in, you'll see that I write about 2 to 3 sentences on each individual item for feedback. So the moment that we get to the Saturday, after you submit it on Friday, on that Saturday at 12:01, all the answers will become available to you. Additionally, my feedback will become available to you, and it'll let you know if we're using a particular formula, what formula are we doing, and all those types of things. So please do pay attention to that feedback. It should be able to help you. And of course, I'm glad to answer emails. I'm glad to do all that, but that feedback is there. It's promptly available to you. It could take me a few hours to respond to an email, but that will be there, and it'll be there for you instantaneously as soon as we pass the due date.